This is the second video in our series on the basic uses of the computer. In our last video, we talked about just using the CPU and memory, and I called that a basic processing unit. In this video, we are going to connect a CPU and memory to a disk device. How does a CPU interact with a disk? Let's do some investigation. And if you did some investigation, you might, for example, start with the C programming language. In C, we have the fopen function, the fread function, and the ioctl functions, and many other functions to interact with the disk. If you dig down into these functions, you will discover layers upon layers downwards. Eventually, you'll reach a syscall that goes into the operating system. If you continue inside the operating system, you will eventually come to an in and out instruction in the x86 architecture, or some other mechanism such as direct access memory, for example. That will eventually lead us to the disk. But let's go back to the basics. What is a disk? Now, a disk is a physical device. It is basically memory that is kept when power is off. So when we turn the computer back on, we still have our data. Now, in order to store something when the power is off, something physical is altered on the disk itself. A disk is basically a list of entries. Now, the entry has a certain size, depending on how the disk was built, and there's a certain number of entries. If we look at this example here, for example, this is a Western Digital disk that is 10 terabyte, that has 10 terabytes of storage. Now, the entry size of this disk might be 496 bytes. This gives us about 2.4 billion entries on this disk. The basic way to interact with this disk is to read any of these 2.4 billion entries or write to any of these 2.4 billion entries. So the commands we can issue to the disk that reflects how a disk works is to get the entry size and the number of entries on the disk. We can then write data to any of these entries, or we can read data off any of these entries. So let's look at each of these three essential instructions in turn. Now, the first instruction might be called entries. This instruction will give us the entry size and the amount of entries. For our example 10 terabyte Western Digital disk, this function would return 2.4 billion and 4,096. The first argument to the function here is the device number. Of course, we might have many disks connected to our CPU. So in this example here, it's the first disk, number 0. The second instruction is a write instruction. Now, the write instruction also takes a device number. In this example, it's 0 again. Then it takes an entry number and data. Now, the data is of the entry size. So for this for the running example, it's 496 bytes. The write instruction might fail for various reasons. So it returns a boolean telling us whether the write succeeded or failed. Now, a reason why it might fail is, for example, that we use a device number that is not available. For example, we issue the number 3, even though there were only 2 disks connected to the computer. The entry size, the entry position that we are modifying might not exist on the disk. Or the disk might have failed. So those are some of the reasons. Now, if this function returns true, the write has been performed. So the data has been persisted on the disk. So we can turn the power of the computer off and the data is still there. And when we get true back, we know that the data has been written to disk 0, entry 0 in this example. The write instruction is similar. Here we also get a device number, an entry number, and the data to read. Or rather an array where we can read data into. The read instruction might return false for similar reasons as the write instruction. The device does not exist, or the entry does not exist, or the device might have failed. But if we get true back, we have gotten the entry into our data array. So these are the 3 essential instructions to interact with a disk. Now, your immediate reaction might be, is that it? What about, for example, open a file, modify control parameters of a disk, buffers, RAID, or partitions, or many other issues that a disk might that you might interact with when it comes to disks. Now, the interesting thing here is that in order to get all this kind of behaviors, we need a program in between our disk and our CPU. So our program running up here interacts with another program that gives some advanced behavior to our disk. But it is still the case that the interaction with the disk itself basically are only those 3 instructions. The program running in between here might expose a virtual disk, and that is a topic we will cover in depth in a separate series of videos. In order to implement these 3 instructions or functions, we will need drivers. Now, there are many kind of drivers we can provide for these. Here I have 4 examples of drivers. For example, we might interact with the system on the disk itself, which might be a SCSI protocol. We can write a driver for these that utilizes the C standard API found in standard input.h. We can interact directly with the Linux files using the Linux kernel, or we can interact with a virtual device, which might, for example, be a network disk. And there are many more options here. Let's look at an implementation where we implement these 3 instructions using the C standard API. We will first need to initialize our file on the disk. In this example here, we enter our main function and we open a file called file.dat. Now, this file was already initialized to be of size 512 times 100,000. We open this disk using read plus, which means read or write, and binary, which means that we will read and write using binary and not the special text mode in C that might interfere with the access to the disk in this example. We then check that we successfully managed to open the disk or the file, and then we run our program that now utilizes only CPU, memory, and the disk in this example implemented using the C API. When our program is done, we close our disk, or we close our file. So this part of the program now has a disk available using the C API, using our simple essentialized interface. Let's look at how we implement our 3 different functions. Now, the entries function is quite simple to implement. We simply return the number of entries and the entry size. The write function is implemented as follows. First, we use fseek to seek to the position on the file that we want to write to. We have to seek entry times the entry size from the start of the file. If this succeeds, which means that it returns 0, we can perform our write using the C API. So we write our data array to the which is of the size entry size, and it's only 1 entry, to our disk. Now, if this write succeeds, we need to call fflush in order to ensure that the data is actually written to the disk. The C API does not guarantee that the write is actually performed on the fwrite returns, but if we call flush, we are guaranteed basically that the write will be performed. Now, only if this call returns 0 can we set our success variable to true. If any of these fail, success is set to false, and the caller learns that there was something wrong using the write instruction. The read instruction is similar. First, we seek the right position in the file. We then read data from the file into our array. And if we get 1 back, which means that 1 entry has been read, return true. Now here's a program that utilizes the 3 devices: CPU, memory, and a single disk device. First, we call entries. We need to learn how many entries there are on the disk, in this case disk number 0, and we need to know the entry size. We then allocate an array of entry size, which means that now we can fill in data into our array and write it, or read an entry from the disk. In this example here, we do a calloc, which means that we set every element to 0. I then write high into the beginning of the entry. The entry is written to entry number 1, and then we read the entry number 1 back. Now, we should have checked that these succeeded, but this gives an essentialized view of how to work with the instructions. So to recap, here we only use a basic processing unit, which means a CPU plus memory and a disk. An important point here is that this program works on any CPU, memory, and disk. The only thing we need is a disk driver. So this disk driver might be going directly towards the actual physical disk, or it might be a more complicated driver, as in this case where we use the C API. So the C API might work on Linux, Windows, and most other operating systems. If we test our program and we see that it works using the C API, it will also work on other implementations which satisfy the interface. This is a simple but powerful disk interface that allows us to do most things with a disk. In the next video in this series, we will look at what happens when, or how we can connect a CPU and memory to a screen, and how we can do essential operations against the screen. If you think the contents of these videos are interesting, then you might want to check out the book which the contents is based on. Thank you.